All right, the fundamental theorem of calculus. Sounds important, doesn't it? Part one. Part one. When I say part one, that doesn't mean it. I don't know why they call it this, the way they did it. But the fundamental theorem of calculus part one is not the first half of the fundamental theorem of calculus. It's its own thing, and then part two is its own thing. They're kind of related, but they're not the same thing. Okay. The fundamental theorem of calculus is probably, you could argue because of the name of it, the most important thing of calculus. Is it? Is it funner? You sound like me. Okay. So, it's pretty basic. We actually already talked about it. Remember on Friday, we talked about the derivative of an integral. What is the derivative of an integral? The integral is the antiderivative. What's the derivative of the integral? It's the function inside called the integrand. So if f is continuous from a to b, so you have to have a continuous function, and capital F represents the integral from a to x of f of t dt, then the derivative of capital F in respect to x is equal to the derivative of the integral. And so that simplifies to f of x. In other words, the derivative and the integral, in a sense, are what? Inverse functions. They cancel each other out. We do have to be careful on one area, though, and we'll talk about that today. Okay? So, that's it. The derivative of the integral from a to x of f of t dt equals f of x. Now, notice, what is the variable in this equation? No. X is the variable. Okay? This t is just a placeholder because the variable is already identified here. Okay? We never have the integral in terms of x and then the integrand in terms of x. This could be anything. It could be f of q dq. But the derivative, or the variable, is just x. And notice what happens here. When I take the derivative in respect to x of the integral from a to x of f of t dt, we do get just the integrand, but what's the variable inside that function? X. It is that, in this case, upper bound, or it's the derivative in respect to x. Okay? It's the variable x. What is a then? A is maybe some constant value. Okay? So, let's look at an example. The derivative in respect to x of the integral from negative pi to x of cosine t dt. What would you say the answer is based on that box statement there? And we'll show why it's true. What do we say? Okay. d dx of the integral from negative pi to x cosine of t dt, you would say is just simply cosine of x, right? Okay, I'm going to show you why that's true. Let's do it step by step. What is the first thing I would do to solve that? Find the antiderivative. So what's the antiderivative of cosine? Just sine. So we would find the antiderivative. So we'd say sine of t from negative pi to x and evaluate that. And then after we're done with that, we'll take the derivative. You guys okay with that? We're just doing kind of an order of operations thing. We're simplifying this expression. Okay? So now what's the next step going to say? Okay, so we're going to plug in the upper and lower bound. And then what? Subtract. So what do we get? Sine of x minus sine of negative pi. And then after that's done, we have to take the derivative, the d dx, right? Are you guys okay with that? Say something if you're not. So what is sine of x? No, what is sine of x? I don't know. What is sine of negative pi? 0, right? Okay. the key to note is that the sign of any constant is going to be a number here, right? And it doesn't matter what that number is. Because the next step is to do what? Take the derivative. And when I take the derivative of a constant, what do I get? 0. Okay. So it doesn't matter that that last term, the sign of negative pi is 0 or not. It could be anything. But the derivative of sine of x is what? Cosine of x. And that's where that comes from. Okay? So the process is you take the integral, figure that out, and then take the derivative of what you have, and then you have your answer. Okay? Now the shortcut is just say, oh, I have a derivative of an integral. It kind of cancels each other out, and we're done. But you do have to be careful, and I'll show you why in a minute. Okay? Can I go on? Okay. So I want you to practice these. And you should know the answers. I mean, you can come up with the answers all by your lonesome using this rule, except for maybe number 3.
You wouldn't put cosine of negative pi.
No, because if you think through the process, we take the integral, so we take the antiderivative, and then we plug in the upper and lower bound. So when I plug in the lower bound, I get something of negative pi, which is a constant. And then when I take that derivative, it becomes 0, and it's gone.
It's not natural log?
Hmm?
It's not natural log?
It's not natural log, no. No. Because okay, let's think backwards, right? You say it's natural log. The antiderivative of that is natural log? Then natural log of what? Okay, but let's check our work. Every time we take an antiderivative, we should take a derivative to see if we're right. What's the derivative of this?
1 over 1. Oh, wait, wait, squared, and then it's...
Because of the chain rule. Right? And that 2t isn't represented in the problem, so that's... yeah, go back in time and don't use pen. That'll fix the problem. All right. So let's see how we did here. And we could go through the proof of this. We will actually. Number one, you should have gotten what? 1 over 1 plus x squared. Because the lower bound is a constant and the upper bound is the variable that we're taking the derivative in respect to, right? So then that means you just get rid of the derivative, get rid of the integral, plug in the upper bound to the integrand, and you're done. But what proves that? You should have recognized, let's say that f of x, just say f of x is 1 over 1 plus x squared. You should realize then that its antiderivative, capital F of x, is, I believe, arctangent of x. These are one of the special functions that had their own rules. We went through them. Let's prove it, okay? Let's go a step back. Remember, anytime you take an antiderivative, oh, what did I miss here? Plus c, right? Because we didn't actually plug anything in. Every time I take an antiderivative, what should I do? Find the derivative to make sure it matches, right? So let's just work with y equals arctangent of x. And we know the derivative of c is 0, so we don't have to worry about that. What do I do here to get the derivative? Tangent of y equals x. Then what? So what's the derivative of tangent y? Secant squared y times y prime equals 1. Derivative of x1. So we got y prime equals 1 over secant squared y. Then what do? Draw your triangle. So you end up with tangent of y equals x. So this is y. Where's x? X is opposite. The adjacent is 1. So what would this be? Rad 1 plus x squared, right? Now when I plug in secant, y prime equals 1 over, what's secant? It's hypotenuse over adjacent. And then when I go to square that, so it'll be, you could argue it's rad 1 plus x squared, but then I have to square it. So it's 1 over 1 plus x squared. So we can see that the derivative of arctangent is 1 over 1 plus x squared. So that when I'm taking the antiderivative of 1 over 1 plus x squared, what are you getting? You get arctangent, right? Okay. So let me rewrite this. Dx of the integral from, what is it, 0 to x of 1 over 1 plus t squared dt. That's going to be equal to d dx of, what's the antiderivative? Arctangent of t evaluated from 0 to x. And we're going to do this part first. So that's equal to the derivative, whatever that is, of the arctangent of what? X minus the arctangent of 0. We don't know the arctangent of x, so we'll just leave that the way it is. What is the arctangent of 0? 0, 2 pi, we just keep the home ones, right? It doesn't matter what it is. It could be 5. Because it is 0, but let's say it's 5. When I take the derivative of that, it goes away. So minus 0, so it's just that. Now the derivative. We just did all the work for this. What's the derivative of arctangent? 1 over 1 plus x squared. So that is that. This is basically one where, okay, we have to take the antiderivative, right? So you have to think in your brain, what function produces that as its derivative? And at first, somebody might say it's natural log because it's 1 over something, right? But every time you take an antiderivative, you should take the derivative to make sure it matches. So I just know from memorization that when I take this derivative, I get that, basically. Okay? So you get tangent on both sides and then go from there. Okay? Now, that's that. The second one is we can't even take that antiderivative at this point. But let's use the rule that we just learned. Is the lower bound a constant? Yes. Is the upper bound the variable that I'm taking the derivative in respect to? Yes. So then the answer is just 3x plus cosine of x squared. You guys okay with that? What about the last one? Okay. Number 1, is the lower bound a constant? No. Is the upper bound the variable that I'm taking the derivative in respect to? No, the lower bound is, right? But if you remember your rules, you can switch it. So we could say that number 3 is equivalent to the derivative of the negative of the integral of negative 5 to x of e to the what? 4th secant of u. Oh, that's a u? Okay. Can't read my own writing. Fair enough. Okay, are we good with that so far? You guys okay with that? Now this negative is now a negative 1 constant, right? Remember, what do I do when I take the derivative of a constant? Like with a constant times something. I can move it out front, right? So I could rewrite this as the negative derivative of the integral from negative 5 to x of e to the u secant u du. Now does my rule apply? The lower bound is a constant, the upper bound is the variable that I'm taking the derivative in respect to. So then what's my answer here?
Negative u to the x.
The negative stays out front and it becomes e to the x times secant of x. Are you guys okay with that? Hey, look at that. I actually showed the same work. Shows my brain works the same way as it did 2 years ago. Are you guys okay with this? Okay. Here's going to throw you for a loop. Any ideas? You got to do something with the 4s. Divide the 4s? Let's look at what your brain is doing, because I know what your brain's thinking right now for most of you. What did we do with that upper bound What do? We just plugged it into the integrand and said we're done, right? The derivative of an integral, we just plug in the upper bound and say we're done. Is the lower bound a constant? Is the upper bound the variable in which we're taking the derivative in respect to? With a 4, right? If it was just x, we'd be good. But I know some of you are thinking, I know, like John just was. So what do? We just take that upper bound and plug it in, right? So what would you get? Well, let's take a step back. It'd be 4x squared plus 1, right? Well, hold on. I'm not saying this is right. But what did I do? I just took the upper bound and I plugged it into the t, like I've been doing, right? Plug in the upper bound to the t and call it good. That's wrong. Okay? Wrong. So let's go about it analytically from the beginning. What would be the first step that you do? Take the antiderivative and evaluate from there. Go. See what you come up with. Analytically, what's the first step we're going to do? So what is the antiderivative of t squared plus 1? 1/3 t cubed plus t. Okay? And the reason we're doing this is because the upper bound is not the variable. It's something else. It's the multiple variable, or it's its own function in a sense. But the antiderivative is 1/3 t cubed plus t, and then we have the evaluate from 4 to 4x, right? Then what do? Okay, so we're going to plug in the 4x to the function, and then the 4, and then subtract, right? You guys okay with that? So that'll be minus, and then more parentheses. 1/3 4 cubed plus 4. And we can simplify this all we want, but what do we know this is going to give us right here? It's going to be 0, so I don't care about that. Well, it's not 0, but when I go to take the derivative of this, it'll be 0, right? So really I only care about simplifying this first part, because that's ultimately the problem. The problem says take the derivative of the integral. So I took the integral. That's what all the parenthesis stuff is. Then the last step will be to take the derivative. So now let's take the derivative of this first thing. 64x. What? 64 x squared plus 4. 64x squared plus 4. What's wrong with this?
How did you do that?
That's the answer.
Oh, wait, never mind.
Took the derivative. You bring the power down to the front and subtract the 1. Okay. Okay. Listen, guys, are we saying that we're taking the integral and that's it? No, we are taking the derivative of the integral. Right? Okay. So why? Let me go back. Why is it different? Well, obviously that 4x, but what happened with that 4x? True, but why did it change it to that? You'll see in a second. Okay, you guys try these. This is good practice with antiderivatives and the like. Obviously, you cannot just use the simple fundamental theorem of calculus because why? What's wrong with this? Because the upper bound is x cubed, not x. So you have to go about it the long way. So go. So what is the first step? What is the antiderivative of secant squared t? Tangent t. So we're taking the derivative of tangent t from 7 to x cubed. So now we're going to plug in the lower bound, or the upper bound and the lower bound and subtract. Right? Tangent of 7, it doesn't matter what it is. It's just a what? Constant. Okay? Now when I go to take this derivative, here's the key. What is the derivative of tangent of x cubed? You could okay, it's secant squared of x cubed and times 3x squared. What's the derivative of tangent of 7? 0. So we could say our final answer is 3x squared times secant squared x cubed. Any connections yet? Look at what's given. What? Take the derivative of the top. And then plug in the top to the variable, right? So t was the variable, so I'm just going to plug in x cubed to t, just like I would have thought. But then I have to multiply it by the derivative. What's that rule called? What rule did we apply here? The chain rule. So the chain rule in combination with the fundamental theorem of calculus gives us our answer. Okay. Now, how does that relate? Let's go back to the previous problem. Let's go back to the fundamental theorem here. How does that work here? If I was going to do that, we said the answer is just f of x. Why? Because the derivative of x is just 1. No, because remember, what's the variable in this problem? X. So if x is the variable, what's the derivative of x? 1. If x was a function, then it would be x prime. But not in this case. Yeah, but x prime, you wouldn't say x prime. The derivative of 3x, which is 3. Right? Okay.
Give me one like that so I can use the fundamental theorem. Oh my god.
All right, you guys try that one then. So let's see here. Dx of the integral from a to 3x squared of tangent of r dr. If you want to do this analytically, do you know the antiderivative of tangent? Is there a function that just gives you tangent as its derivative? No, there's not. Okay? So we have to think about this different. Well, we just went through a problem like this, right? Does anybody think they have an answer? Okay. So what do? We say tangent of 3x squared times the derivative of the upper bound. Right? In theory, that should be what it is. How can we prove it? Thank you for that insight. No. It's a theorem, and if you learned in geometry, theorems are those things that are provable. Right, the vertical angle theorem? Yeah. What is wrong with this? You remember? No, you don't remember? Why did the internet just all of a sudden go down? Apparently not. All right, we're gonna have to go off the whiteboard here. Okay. So I guess here's the question that I would ask. Okay. Since we do not know the antiderivative of tangent of r, so this is what we're saying our answer is. Let me show the analytic work. Okay. Do you know the derivative or the antiderivative of tangent of r? No. So let's just say that f of r, big F of r, equals the antiderivative of tangent of r. No, I'm just showing you where it comes from. Are you guys okay with that? I don't know what the antiderivative is. And in all reality, you cannot take the antiderivative of every possible function. You can't. You can take the derivative of every function, but you can't take the antiderivative. So let's just say this represents the antiderivative, right? Okay. What would this equation, ignore the derivative for right now, what would this part be if the antiderivative was f of r? It'd be capital F of r. What? Evaluated from a to 3x squared, right? And then we have the derivative out front. We'll get to that later. What would this be then? F of 3x squared minus f of a. And again, we'll take the derivative of that later. Actually, we can take the derivative of that now. So A is a constant. Okay. So what is the derivative of f? How would we write that? F prime of 3x squared times 6x, because you have to apply the chain rule, right? Minus, what's the derivative of f of a? 0, because f of a is a constant, right? A is a number, therefore f of a is a number, right? So then, now we go back up here. What is the derivative of f? If capital F is the antiderivative of tangent, then the derivative of f is the tangent of, well, what was r in this case? And then the 6x can go up front. That's our answer. Are you guys okay with this? What is this? This is kind of the proof for why this way worked, right? So, in other words, the fundamental theorem of calculus, I guess, in a nutshell, in one aspect, there's other parts to this. The derivative of an integral is the integrand, but what do you have to do? You have to plug in the upper bound into the variable, and then take the derivative of that, and then multiply them together. What was that called again when we take the derivative of the upper bound? The what? Why did I take the derivative of 3x squared over here? Because of what? The chain rule, right? So it is the chain rule infused with that. Brandon, you had a question.
Would you or the and or if testers like to see it like on the right or on the left?
No, you should automatically know that this leads to this. But what you have to be careful of is so many students will just say, oh, it's tangent of 3x squared, and leave it like that. Because they're just taking the derivative of the integral, they just take the upper bound and plug it in, and we're done. No, you have to take you have to plug in the upper bound, and then take the derivative of the upper bound. Okay? Are you guys okay with that? Okay. What's the rule going to say? The bottom number is a constant. The upper number is, you could say, its own function, right? It's not just x. It's its own function. So what do I do when the upper value, or the upper thing, is not just x? The derivative of that would imply cotangent of what? 3 times rad x, and then what? Times the derivative of this, right? And, I mean, you could write it as x to the 1/2, but it's simplified. The derivative of that is 1 over 2 rad x. That's it. Okay? Or in other words, cotangent of 3 rad x all over 2 rad x. Okay? What's wrong with this one? The variables, the functions on the bottom, the variables on top, right? This, remember, these values inside are just placeholders. They're not the variables.
Is this plus or
T 2 plus p squared. Okay, so we would say, I'm going to rewrite this as the negative integral from 10 to 3x squared of natural log of 2 plus p squared dp. Yeah, stay. Stay or don't learn. It's up to you. So, help me out here. Help me out. Natural log of 2 plus 3x squared squared times 6x. We're missing one thing. The negative out front. Okay?